state and prove the famous L'Hopital's rule. Right? This is something that we have been using since our first encounters with calculus. The goal of this video is to not just state it formally, but also go over the proof, which if you are able to look through the various cases and subcases to consider, the core argument is actually remarkably straightforward. Okay, so what is the statement of L'Hopital's rule? Let S is the point at which we are going to consider the limit. So let S signify either A plus, A minus, infinity or minus infinity. Okay, where A is real valued at this point. And moreover, suppose that f and g, two functions, are differentiable. It's unspecified here, but clearly this means they are differentiable in some neighborhood of S, right? Suitably. And you have the following holding. First, you need that as x tends to S. Again, depending on what S is. So if S is A plus, that means that this is the right limit at A. If S is A minus, it's the left limit at A, right? So as x tends to S, if you have that the ratio of f prime to g prime is equal to L, okay, that's the first. So the ratio of the derivatives tends to L as x tends to S, right? And in addition, you need either one of 2 or 3 to hold. 2 corresponds to the so-called 0 by 0 case. That is, as x tends to S, both f and g should tend to 0, right? And 3 corresponds to the case where g, absolute value of g, tends to infinity as x tends to S. Now, in this case, we don't need to explicitly assume that absolute value of f tends to infinity as x tends to S, because that, it turns out, will be implicit from the other assumptions. Okay, so if one holds and either of 2 or 3 hold, then in fact you have that as x tends to S, the ratio of f of x to g of x tends to L. Okay, and that's the conclusion of L'Hopital's rule. So essentially, it lets you conclude the limit of the ratio of f to g as x tends to S in terms of the limit of the ratio of the derivatives, right? Given that either 2 or 3 hold, you either need to have that both f and g tend to 0, or you need to argue that in absolute value g tends to infinity as x tends to S. Okay, so that's the statement of L'Hopital's rule. Now, the statement has been written somewhat compactly. Let me just highlight what some of the implicit assumptions that are built into the theorem are. So the fact that 1 is assumed to hold implies that, remember, f and g both have to be differentiable in some suitable neighborhood of S. Implies that f, g are differentiable in a neighborhood, and this too has to be suitably interpreted, right? Because, so for example, if S is A plus, that means that in some open interval from A to B, let's say, where B is larger than A, f and g are differentiable, such that the derivatives f prime and g prime are well defined in this open interval, right? So f and g have to be differentiable, and moreover, for the ratio of the derivatives to be well defined, I need the g prime x is not 0, again in a neighborhood of S. Right? Because for the limit claimed in 1 to hold, you need f prime by g prime to be well defined, which means that both f prime and g prime are well defined and g prime is not equal to 0. Alright, so that's implicit in the statement, so I'm just highlighting that before we get into the proof. Okay, so now let's start with the proof. Okay, now the proof has a whole bunch of, if you look at the statement, there's a whole bunch of cases with respect to all the different possibilities for S. So what we are going to do is restrict ourselves to the case where S is either A plus or minus infinity. Now, why are we considering these two cases? Well, these two cases can be considered in a unifying fashion because both when you're looking at a plus and minus infinity, the limit is obtained by x approaching from the right. Right? In the case of a plus, you are approaching a from the right, and in the case of minus infinity, well, you are approaching minus infinity from the right. Right? So there's a right approach involved in the limit, and so that's why these are the two cases we will consider together. An analogous argument also applies to a minus and plus infinity. Right? These would be those two cases where the limit is obtained via an approach from the left. Right? And moreover, once you have the argument for a plus and a minus, it follows that it applies to a. So argument for a plus and a minus implies the argument for a. Right? All of this is basically to justify our restriction in the following to simply a plus and minus infinity. Alright, so these are the two cases that we will consider in the proof. So we will prove the following statement. We will prove and in the remainder, I am going to it's going to be a unified argument for a plus and minus infinity. So you will just assume that a is either in R or minus infinity. Okay, this is simply to write a single argument that applies to both cases, right? Given both of these, we have to prove two statements. Now, what is it that you need to prove? That if you take any number that is larger than the limit, then if x is sufficiently close to a, then f by g will in fact be upper bounded by that number. Similarly, you need to prove a lower bound, right? So we are going to do is separate these two statements. So statement 1 is going to be the upper bound. If the L, the limit of the ratio of the derivatives, lies in this set, that is excluding plus infinity, because if you are at plus infinity, you don't have to prove an upper bound, right? For L1, which is greater than L, there exists, let's say, an alpha 1 which is greater than A, such that A less than x less than alpha 1 implies f of x by g of x is less than L1. Right? So this is the upper bound. That is, if you pick any L1 which is larger than L, then there exists some alpha 1 such that if you are sandwiched between A and alpha 1, then f of x by g of x is less than L1. In other words, if you pick any L1 which is larger than L, then being sufficiently close to A from the right will imply that f of x by g of x is less than your upper bound. Right? So this is one of the statements required in order to prove the result. The other statement is, of course, the lower bound. So that's statement 2. If L lies here, right? You don't need to prove a lower bound if L is minus infinity. Then for L2, which is less than L, there exists again some alpha 2 which is greater than A, such that A less than x less than alpha 2 implies f of x by g of x is greater than L2. Right? So what this means is that if you pick any number which is less than L, then being sufficiently close to A from the right implies that f of x by g of x is greater than L2. Right? Convince yourself that if S1 and S2 both hold, then in fact the statement of the result holds, namely that the limit of f of x by g of x is equal to L. Okay? So let's call the statement 4. So the first thing to note is that S1 and S2 imply 4. Okay, and moreover, we will focus only on S1. Right, the argument for S2 is also analogous. So if I just prove S1, that's sufficient. All right. So in our goal in the remainder of this proof is to basically prove statement S1. That is, assuming A is either in R or minus infinity, and assuming that L is between minus infinity to infinity, minus infinity included. For any L1 greater than L, there exists some alpha 1 such that being between A and alpha 1 implies that f of x by g of x is less than L1. Alright, so this is what we want to prove. So now let us first look at some immediate implications of the hypothesis of the theorem itself. Now the first thing to say is that let the interval AB be the region over which the derivatives are well defined. B interval over which f prime g prime are well defined and g prime does not vanish. Okay, this is the interval over which, let us say, the f prime by g prime is basically well defined. So both f prime and g prime are well defined and g prime does not vanish. Now the fact that g prime does not vanish implies that it must either be positive throughout or it has to be negative throughout. So g prime x is either less than 0 for all x in AB, or g prime x is greater than 0 for all x in AB. And why is this? This is because of the intermediate value theorem for the derivative. Right? We know that the derivatives, in spite of the fact that the derivative of a function need not be continuous, derivatives satisfy the intermediate value property. So the fact that the derivative never takes the value 0 implies that the derivative must either always be positive or always be negative over the interval a to b. Okay, so again, without loss of generality, we assume that the derivative is negative. Why without loss of generality? Well, if not, just multiply g by minus 1, right? Just multiply both f and g by minus 1 and then you would end up having this. So this is basically a without loss of generality assumption. Now, what does it mean to say that g prime x is negative over this entire interval? That means that g is strictly decreasing. Okay. Now, what is the implication of g being strictly decreasing? If g is strictly decreasing over this open interval, then g can possibly take the value 0 at most once, right? Somewhere in this open interval, which means that by shrinking b even further down if need be, I can basically restrict myself to an interval where even g doesn't take the value 0. So this implies that by shrinking b if needed, we may assume that g of x is not equal to 0 for all x in the interval AB. Okay, so to summarize, what we have said so far is we are trying to prove the statement S1. And what we have first said is that the fact that g prime does not vanish implies that g prime is either positive or negative throughout. Without loss of generality, we assume that g prime is negative. And moreover, by suitably restricting B if needed, we know that G is also not 0. Sorry, I should say not 0. Okay, so over the interval a b under consideration, G prime is negative and G is not 0. So these are the things to keep in mind. Okay, so this is most of the groundwork that we need to make the actual arguments, which we'll show on the next page. Alright, so now we have to prove the statement S1, which is the upper bound. So to do this, let us first pick some number k, which is less than L1. So pick k such that L is less than k is less than L1. Okay, so by the original statement, remember statement 1 told you that the ratio of the limits, ratio of the derivatives, that is f prime by g prime tends to L as x tends to s, right? So by 1 that implies that there exists an alpha greater than a such that a less than x less than alpha implies that f prime by g prime is in fact less than k. Alright. Now we apply the generalized mean value theorem. Right, so in the interval from a to alpha, if I pick any two numbers x and y for a less than x less than y less than alpha, then the following must hold by the generalized mean value theorem. That is f of x minus f of y upon g of x minus g of y is equal to f prime gamma by g prime gamma for gamma between x and y. Okay, but since gamma lies between f and between x and y, it follows that the ratio f prime gamma by g prime gamma must also be less than k by the statement just above. Right. So therefore, what we learn is that for a less than x less than y less than alpha, it is true that f of x minus f of y upon g of x minus g of y is in fact less than k. Okay, so this is, let's call this statement 5. Now we are going to prove the desired limit of f by g by considering either of the two statements, either 2 or 3. Okay, so now let's do that bit. So suppose that 2 holds. Right, what is 2? Well, 2 means, recall that limit x tends to a. Here I'm implicitly, I should have technically say a plus or minus infinity. So let me just say a here, just to remind you that f of x is equal to 0 and limit x tends to a, g of x is equal to 0. So that's the statement number 2. If this holds, then all you have to do is look at equation 5 and let x approach a. So let x approach a from the right, of course, in 5. Once you do that, since as x tends to a, f of x and g of x both vanish, it now follows that you have that f of y by g of y must be less than or equal to k for y in the interval from x to alpha. Right, and that really proves the statement S1. This proves S1. right? So once you've given equation 5, if hypothesis 2 holds, it therefore follows that the statement of S1 also holds. That is, that we are able to upper bound. So remember, this K is in fact less than L1, right? That's why the argument holds. So we have basically proved that the ratio F by G is in fact upper bounded by whatever L1 you choose that is larger than L, so long as Y is sufficiently close to X from the right. Okay? That's exactly what we have proved. So this basically completes the proof, assuming that hypothesis 2 holds. Now we will consider what happens if hypothesis 3 holds. So if 3 holds, right, what is 3? 3 means, remember, limit x tends to a. Well, I should have said x tends to s, where s is either a plus or minus infinity, right? Let's assume that you understand that. Limit x tends to a mod g of x is equal to infinity. So suppose the 3 holds. Now, before we get into the details here, let us first understand what it even means. Remember that we have already supposed that g prime is negative, which means g is strictly decreasing in the interval from a to b, and g never takes the value 0, right? So it is strictly decreasing, does not take the value 0, and as x tends to a from the right, absolute value of g is equal to infinity, right? This could only possibly happen if in fact g is actually itself being pushed off to infinity. Sorry, g of x is equal to infinity and g of x is greater than 0 for all x in AB. Right? Why is this? G can never actually take the value 0 and g is strictly decreasing. The only way g could be strictly decreasing and tend to infinity as you approach a from the right could be if it's actually approaching plus infinity and g is positive throughout, right? So yeah, so keep this in mind that g by our hypothesis is actually positive throughout if 3 holds, and the limit is actually plus infinity, for g itself without the absolute value, wrapped around. Okay, now we are going to go back and apply equation 5. So from 5, what I want to do is, I want to separate out f by g. Okay, so what we are going to do is write it as f of x minus f of y upon g of x is less than k times g of x minus g of y by g of x. Now, why am I allowed to do all this multiplication on both sides of 5? Well, what I'm multiplying by is positive. Remember, g of x is positive, and moreover, g of x minus g of y is also positive because g is strictly decreasing. Okay, so therefore, the inequality we have just written does in fact follow from 5, given that g is strictly decreasing and positive over the interval under consideration. Okay, so now you just massage this a little bit more and see that this implies that f of x by g of x is in fact less than k plus f of y minus k g of y upon g of x. So all we have done is separated out f of x by g of x on one side. Now the thing to note is that treating y as being fixed, and if you just take x tending to a, well, the fact that g of x tends to plus infinity implies that this latter fraction actually tends to 0 as x tends to a, right? Which is essentially what we want, right? So treating y to be a constant, letting x tend to a, we conclude the following, right? So f of x by g of x is less than k plus something that tends to 0 as x tends to a. What does that mean? That means that once x is sufficiently close to a, f of x by g of x should be less than k plus something arbitrarily small, right? And L1, remember, is larger than k. So therefore we can now conclude that there exists an alpha 2 which lies further between x and alpha, such that f of x by g of x is in fact less than L1 for x in the interval from a to alpha 2, right? Which is exactly what it is that we wanted to prove. So this proves S1. Okay, and that in turn completes the proof of the statement. Okay, so if you think about it, there's a lot of cases to be discarded and considered carefully, but the main crux of the argument is basically inequality 5. And inequality 5 in fact follows from an application of the generalized mean value theorem. So once you have the inequality 5, then all you do is apply the hypothesis, which is either 2 or 3 that you have, to argue that therefore the limit that f of x by g of x is in fact upper bounded by any number L1 which is larger than L, so long as x is sufficiently close to a from the right. Right? As I said before, an analogous argument applies to prove the lower bound statement S2, and combining these together, you basically have the proof of L'Hopital's rule. Okay, so in this video, we'll stop here. In the next, we will look at some examples of applying L'Hopital's rule.